In the natural world, electricity is a chaotic discharge of static energy. A lightning strike releases immense power, but it is fleeting and entirely unusable. To power a society, that raw energy must be converted into a continuous and predictable flow. This requires an organized network designed to capture, transform, and distribute energy across thousands of miles. The central challenge of electrical engineering is a problem of control. We must mathematically quantify and physically route billions of subatomic particles to perform macro-scale work in our homes and cities. To build a functional model of how this happens, we have to define 4 specific variables: charge, current, voltage, and resistance. We also have to account for topology. The physical geometry of a circuit dictates exactly how those variables interact and behave. The movement of this energy depends entirely on the physical conditions we create. Without a continuous path and a specific potential difference, the charge remains trapped or dissipates before it can turn a motor or light a screen. Understanding the power grid requires looking past the heavy machinery to analyze the foundational physics of a single moving particle. The physical foundation of electricity begins inside the atom. Our focus is on the electron, the negatively charged particle in orbit around the nucleus. In a neutral conducting material, like a piece of copper wire, free electrons move randomly in all directions. Because this motion is scattered and lacks a net direction, the overall electric charge of the conductor is 0. To measure the capacity for electrical work, we need a standard unit to quantify these electrons. We call this unit the Coulomb. 1 Coulomb is massive, exactly 6.25 times 10 to the 18th power electrons held in an imbalanced state. When we attach a power source, we force this massive charge out of its random state, compelling it to move uniformly in one direction. This is the mathematical definition of current, represented by the letter I. Current is the continuous rate of this charge flow, calculated by taking the amount of charge, Q, and dividing it by time, T. The ampere, the standard unit of current, represents a physical reality. 1 ampere means precisely 1 coulomb of charge has passed a single point in the circuit in 1 second. Charge does not move uniformly on its own. There must be a driving force that compels the coulombs to flow. Voltage, V, is a measure of electrical potential difference. It is the exact amount of work required to move a unit of charge. Mathematically, it is work divided by charge. Because electrons are negatively charged, applying voltage physically pulls them toward regions of higher potential. This diagram highlights a historical quirk in notation. The physical reality is that electrons move from the negative terminal to the positive. However, conventional current is drawn moving in the opposite direction. As electrons move, they experience friction within the conductive material. This physical opposition is called resistance, measured in ohms. Materials with loosely held electrons, like copper, offer low resistance. Insulators, like rubber, hold electrons tightly, presenting high resistance that requires significant voltage to overcome. The actual flow of any electrical circuit is a continuous physical negotiation. The applied work of the voltage pushes the charge, while the material's inherent resistance opposes it. Once we understand the variables, we can manipulate them through topology. The physical geometry in which we arrange components dictates exactly how voltage and current are distributed. A series topology connects components end to end, so they share a single continuous path. These string lights are a common application of this layout. In a series circuit, current has only one path to flow, so it remains constant through every component. However, the total voltage divides across each resistor in the sequence. This topology has a critical vulnerability. If a single component fails, if one bulb fuses, the path breaks and the entire circuit goes dark. Parallel topology solves this by wiring components so they share 2 common nodes. This creates multiple independent pathways, as seen in this household breaker panel. In a parallel circuit, the current splits and divides among the paths, but the voltage across every branch remains identical to the source. Because each branch acts as an independent circuit, parallel topology offers resilience. If one device fails, the neighboring components continue functioning without interruption. Engineers use series circuits, like fuses, to control power by restricting flow, and parallel circuits to deliver constant voltage to multiple devices. The final variable controlling our electrons is modality, the directional nature of the current over time. Direct current, or DC, is unidirectional. Electrons flow steadily in one direction, maintaining a constant voltage without reversing. This is the output provided by batteries. Alternating current, or AC, is bidirectional. The movement of the electric charge periodically reverses its direction entirely. This chart graphs an AC sine wave. At the standard 50 Hz, the wave completes 50 full cycles every second. Since the wave crosses zero twice in every cycle, once to swing positive and once to swing negative, the current reverses its direction 100 times every second. Whether AC or DC, the ultimate metric of electrical engineering is power. Power is the rate at which electrical energy is transferred to do tangible work. When we multiply voltage, the work per charge, by current, the charge per second, the Coulomb variables cancel out. This leaves us with work over time. Power equals voltage times current. Measured in watts, power represents the physical capability of a circuit. It tells us how much mechanical work those electrons perform in human seconds. This map illustrates how these theoretical principles scale to construct the global energy infrastructure. Every stage of the grid, from the plant to the home, is an application of the relationships between voltage, current, and topology. At the generation phase, physical forces like moving water are captured. This creates the initial voltage differential needed to push charge into the network. During transmission, alternating current is utilized to push this power across vast distances. High voltage AC allows engineers to move energy efficiently despite the resistance inherent in miles of wire. At the destination, the architecture must shift. A few massive transmission lines branch out to serve millions of localized, individual paths. Parallel topology is required at this stage to ensure that every appliance receives a constant voltage, independent of every other device in the city. Mastering electricity requires understanding more than just a physical phenomenon. It is an understanding of the mathematical architecture of work, time, and topology that spans from a single electron to the global grid.